Salt damage is a little bit similar. Water is also involved. The decay mechanism also occurs in porous stone, but we have to think a little bit carefully about the salts because there are a range of different types of salts. There are different chemical formulae to the salts, and there are different amounts of water associated with the salts. There are both hydrated and unhydrated salts. We see here damage to a wall painting. This damage is caused by the efflorescence of potassium nitrate, and potassium nitrate is an unhydrated salt, so the damage is probably a little bit more superficial than with hydrated salts. How does this damage occur? Well, what happens is it's the humidity, really, is the principal driver of salt damage. Changing humidity, the daily cycle of humidity, the seasonal cycles of humidity tend to cause this salt damage. Temperature can also be involved, as we'll see, but humidity is the real problem. And when it requires that humidity passes a certain threshold, so we can imagine that where we've got a brine, some salty water inside a porous stone, and gradually the humidity falls and it dries out that brine. The brine crystallizes, and it's those crystals that exert pressures on a stone or a piece of masonry. And this occurs usually at a very specific relative humidity. So every time you cross that relative humidity, you get a crystallization event or an event where the crystals dissolve and form a brine. And with the case of sea salt, sodium chloride, this occurs very close to 75% relative humidity. So you can see in this particular set of data, you can see how, a few times each year there's a transition to a drier, lower relative humidity, and crystals form, and so this leads to a salt crystal forming and thus salt weathering. Now we can look at the nature of these salts through X-ray diffraction, and what I show you here is a group of minerals that were found in an efflorescent salt on the surface of stone in a sort of subterranean passageway. And what we see is a range of salts. We see thenodite, mirabolite, aphytolite, niter, and arapskite. What you'll notice is, if you look closely at those formulations, the chemical parts of the formula, the actual salt itself is shown in purple. But what I've added is the green shows the number of water molecules associated with the salt. And mirabolite has water molecules associated with, as does darapskite. And you're going to see these water molecules are really, really important. So here you see the salt damage caused by thenodite and mirabolite. Thenodite and mirabolite are sodium sulfates. The mirabolite has water associated with it, and the thenodite has no water associated with it. The mirabolite is a much bulkier salt. It has a much greater volume with all this water inside the salt. So if we converted from thenodite to mirabolite by adding water, the salt would expand enormously and shatter the stone. This is just what's happened here. Aphytolite, on the other hand, has no water associated with it. So its presence is just as this very thin layer. Certainly it's aesthetically displeasing, but it's not actually going and damaging the surface of the stonework. And these two pieces of damage, the mirabolite-thenodite damage and the aphytolite damage, are probably less than a meter apart in this particular passageway. And yet one's causing very, very little damage, the other is causing enormous damage. So let's look at what's driving this. Firstly, in this phase diagram, we can see that aphytolite, the aphytolite changes its transition between a salt and a brine hardly varies with temperature at all. But what we can see is in the case of the mirabolite-thenodite transition, This is really strongly dependent on temperature. So if we go to high temperatures, most of the salt is present as sthenodite. If we go to low temperatures, we get much more mirabolite. But also we can see there's a humidity variation to this. So what I'm going to do now is to take this particular mirabolite sthenodite phase diagram and show real climate plotted on that data, because every time you cross between sthenodite to mirabolite, you get a salt that expands and exerts perhaps 10 megapascals of pressure on stone, which initiates cracking and delamination, and this is a really important process. So this transition, sthenodite to mirabolite, and what you can see is that in some climates, so the climate here, the little white dots with the black lines around them, that particular climate, it's just mirabolite the whole time. So there's no particular change in the volume of the sodium sulfate crystals. However, in the climates marked in blue and in red, they occupy all the regions across there. Sometimes they're sthenodite, sometimes they're mirabolite, and every time they cross from sthenodite to mirabolite, they exert enormous stress on the rock in which these brines exist. We can also think about salt crystallization in terms of a more familiar climatology, the Köppen climatology, and here we see modeling of salt crystallizations, a number of salt crystallizations for sodium chloride, an unhydrated salt in Spain each year, and what we see is that the largest number of transitions are found right along that northern coast of Spain near Asturias and provinces like that. And that particular northern part of Spain has a very unique climate. What we can see is it's a CFA or a CFB climate. It's a more moist, humid, variable climate. And the rest of Spain is, by contrast, comparatively dry, so we see very few salt crystallizations each year. So what we'd expect here would be, we would expect salt damage to be quite important in this very northern part of Spain. So the Köppen classification here is really quite successful at kind of predicting this particular form of damage, even though Köppen didn't include relative humidity, which is so critical to salt damage. Salt weathering can also occur through salts in the soil, and this is the case for the salts, for example, that are found around the pyramids of Egypt, but it's also known in Arctic buildings, in the high Arctic. The explorers' huts often have salt damage to the wood, although this salt usually arrives from wind-blown salts from the sea. But we shouldn't always think of salts simply oscillating in terms of the way in which they crystallize and go back to brines. They're more complicated than that because they can rise from the ground up to considerable height.